I call it the truth about p-values. That's a very bad name, but I cannot think of a better ones. Okay, so here's a joke from a paper, and the joke is, why do so many colleges and grad schools teach the p-value equal to 0.05 threshold? The answer is because that's what the scientific community and journal editors use. And the question is, why do so many people use p equal to 0.05? The answer is because that's what they were taught in high school, right? College or grad school. This is a joke, right? But it's essentially telling how norms are continue in every discipline. Okay. The problem with p-value is that there has been growing concern about the issues of reproducibility and replicability of scientific conclusions. Many scientific research are published because their results are significant, right? According to a p-value that is below a threshold, let's say 5%. Okay. However, that could often lead to a lot of problems. There's another quote by another paper that says, statistically speaking, science suffers from an excess of significance. Okay. And this is another pretty famous paper that says why most published research findings are false. And here by false means they are not reproducible, they're not replicatable, and often the results disappear if you do it again. And essentially the author says that one of the reasons is an over-reliance on p-value alone to decide whether research should be published or not. Andrew Xiamen, a very famous statistician at Columbia, who was very famous for his blog actually. He writes he's a very good writer. Okay? He writes a very good blog. I recommend every one of you to check out, because he often talks about social science research, including economics, political science. He does a lot of political science himself. So he's partly, I think he has joint appointment in the statistics department and the political science department at Columbia. So he's kind of like a social scientist. But there is a discipline in social science that he really dislikes, and that is psychology. So he often writes about how bad research are published in psychology. I'm not going to wade into that, but this is what he actually writes in one of his papers, which says, top journals in psychology routinely publish ridiculous, scientifically implausible claims justified based on p smaller than 5%. And this in turn calls into question of all sorts of other research, etc. And I'll give you examples of the so-called ridiculous research that Andrew Xiamen is talking about here. We'll see very soon. Anyway, so there has been quite a controversy about how we use p-value and interpret p-value in the correct way. So much so that there are a lot of papers written about it in recent years, and the American Statistical Association actually came out with a symposium, the formal statement on how we should actually interpret p-value. So this kind of there's a large fight, or there's a large discussion in the statistical community. And in this lecture, I'm going to give you a summary about essentially the meaning of p-value, the limitation of p-value, and the misuse of p-value, as well as how we should interpret or approach our own scientific research. Okay, and this is potentially an issue larger than economics, because it is used in every statistics-based discipline. Right? Okay. Now, first of all, what exactly does statistical inference do? Right? It's essentially telling you, it deals with a very, very narrow question. Statistical inferences really deal with the problem of uncertainty in our estimate, because we have limited sample, right? So we have limited sample. Our sample varies every time we draw a sample from the population. So essentially deal with a very narrow problem of quantifying this uncertainty due to sample variability. And for linear regression, we reach this formula for our t statistic, right? So in large sample, it can approach a normal distribution 0, 1. In finite sample, we don't know what it is, unless we assume the E is a normal 0, unless we assume the E is a normal distribution. If we assume E is normal 0 sigma square, then we know this t statistic is a t distribution in finite sample. If we do not assume that, we don't know what it looks like in finite sample. But we know in large sample it approaches a normal distribution, normal 0, 1, like this. And therefore, based on this, we can calculate a p-value, right? So the p-value is, what is the probability of we observing the absolute value of t larger than what we see from the data. Okay. Now, that brings us to, I'm going to skip these because I'm sure that you all know what they mean, right? The rejection of H0 doesn't mean it's really different from 0. It could be a very small number in absolute value. Just we know that it's not 0. The rejection of H0 doesn't mean X has a significant causal effect on Y. So anytime it's significant is really bad word. Unfortunate, right? It's a historical word. It's unfortunate we call it significant, because that often makes people think that when I say this variable, this beta is significant, it just means that we, using hypothesis testing, we reject it now, right? We say, okay, we accept the H1, which is this thing, this beta is not equal to 0. That's all it is in the underlying population. It doesn't mean that it has a large effect. It doesn't mean that it's really significant to Y or whatever, right? So that often leads to a lot of unfortunate misunderstanding. But that's not a main point in this talk. So I'm going to skip it. One thing that even people who are very familiar with this with statistics or being taught very well often forget is this. Whenever we are talking about the significance of a beta or the interpretation of a certain beta, it's always with respect to a specific model. Okay? So what I mean is that if I have Y equal to beta 0 plus beta 1 x1, well, let me just say beta 2 z, okay? And then I find out that, look, this beta is positive and also statistically significant. And then I say, okay, so many people go from here to say, I conclude that X has a significant effect on Y. Well, whenever this beta is positive, significant, it's always with respect to this specific model. Meaning, if I change this model, we may no longer have the same beta 1, and the beta 1 may not be significant anymore, right? So if I do not use Z, if I change from another variable W, that's a different model. And in this case, beta 1 may no longer be statistically significant or has the same sign or whatever, right? Or maybe let me just get rid of it, okay? Then we can have a completely different beta 1. So anytime when you're discussing the effect, okay, the effect of this, effect is another bad word, because statisticians use the effect a lot, but econometricians economics, we say effect is a causal effect. But in statistics, right, when we talk about effect, that's all very bad word. But anytime you talk about the effect of X on Y, you should always be clear that this is within your model, okay? Within this model. If you change the model, it no longer exists, right? So that's a clarification. And also, when we do empirical research, we should always be clear. When we say we accept the null or we reject the null, say we reject the null, the beta is not 0 in the underlying population. That's our judgment. If we do that, it's always with respect to an underlying population. Okay. So when you say beta is not 0, according to your judgment, right? When you do hypothesis, you say I reject the null, beta is not 0. You're saying that beta is not 0 in the underlying population. But what is underlying population? The underlying population is the population that your data is randomly drawn from, right? So if your data is not randomly drawn from that underlying population, then you cannot say anything about that underlying population. And that trips people a lot. So in this case, we can always talk about study population, target population. Study population is the underlying population that your data is actually drawn from. Target population is the population you want to say something about. And if they're not the same, then you cannot simply go from study to target population just by imagining things. You cannot just go directly there. That brings us to a lot of psychology research, right? Also behavioral economics. It's very similar. So people do psychology research or behavioral economics, behavioral finance in labs. And when they do lab, they give people some experiment and they reached the conclusion. The conclusion is, look, if I give people this coupon, they will have a statistically significant effect on people's perception of something. Okay, so that's a typical research. What is the people here? Now, even if you say even if your statistical significance conclusion is correct, what is the people? You say if I give people this incentive, according to my experiment, they have a statistical significant effect on people's thinking about this. What is the people? Well, it turns out that if your experiment subjects are mostly American undergrad people, not American, but mostly undergrad students, then the effect should only exist in the population that your data is drawn from, in the sense that it should only exist in the population of undergrad students in your college. It's very hard to say that such an effect exists anywhere else in the world. Okay, so there's a saying that psychology is the study of psychology students, because in psychology, majority of research are conducted on undergrad students, psychology students, actually undergrad students who major in psychology, right? So in the end, that's the underlying population we're talking about, not the entire humans, population in the world. Okay. And in order, so it's that brings to the, we'll talk about external validity, internal validity, these concepts later in this course. But here what I want to emphasize is that even if you conclude something is significant, is non-zero, accept the alternative hypothesis in the underlying population, you still should be very clear about what your underlying population really is. Okay? Does that really allow you to say something beyond that specific population? Okay. But anyway, I'm going to begin discussing the true point I want to talk about p-value. We're discussing this in terms of what p-value truly means. Okay. All right. Before talking about what p-value, the true interpretation of p-value, let me give you an example of ridiculous research that Andrew Gallman talked about when he said, okay, psychology routinely publish ridiculous results. So here is one ridiculous result that's published in a top journal in psychology. And that's the famous ESP study by a psychologist at Cornell. And so this guy, Darabam, he became famous because of this study. What he did is he published research saying people have ESP. ESP stands for extrasensory perception. Basically it means that he says people can predict the future in some situation when they shouldn't have no ability to predict. They can sense the future. So he did this experiment. That's a true experiment, if I recall correctly. He put some Cornell undergrads in a lab, and he divided those people, like an experiment, divided people into two groups like that. And he showed people pictures, right? Pictures of different things. And he tries to ask people whether they can predict the pictures randomly generated by computer. So he tried to ask people whether they can predict what kind of picture they will see the next. So the picture of two give you an example. This is actual performance he did, right? Actual experiment he did. He tells students, okay, the next picture you're going to see there could be nudity, okay? There could be erotic picture, or non-erotic pictures. There could be sexy erotic picture. So so if the male guys can show nude girls or whatever, right? So it could be sexy nude pictures, or it can be just a normal picture. Can you guess whether you're going to see a erotic picture or non-erotic picture? And he finds that statistically significant. So if the two pictures are not erotic versus non-erotic, if it is like landscape versus non-landscape, the people do not have this sensing the future ability. But if it's erotic versus non-erotic, he says statistically significant effect on people's ability to predict whether they will see erotic or non-erotic. Right? So in the end, I think the data, I forgot the data, but data is something like 53% of men will correctly predict whether they will see erotic or non-erotic picture. And he did his analysis. Its p-value is below 0.05. And he said, look, there's statistical significant ability. People have this statistically significant ability to predict, to sense the future when they know there's something exciting happening, like going to see about a picture. Okay, so that's his experiment, and from that he concludes that people have ESP, actual sensory perception. Now, obviously, that is a ridiculous paper to write. Right? It's a ridiculous result, and nobody should take it seriously. But it's published in the top journal in psychology, and that, of course, and then they actually bring a lot of journalists. The journalists sort of, New York Times reported. So this is a New York Times article, right? So New York Times reported on this research. It became famous, and of course everybody started to say, what's wrong with this guy, or what's wrong with the research? Essentially, the question: what's wrong with the research? Why is this article published? This guy, Darren Baum says, look, my research methodology is all here, and I did my research, and it's statistically significant. So what can you do, right? It's statistically significant. So that's why we should reject the null hypothesis, accept an alternative, and say people can sense the future. So I'm going to tell you why that is a bad practice, right? I'm going to tell you what's wrong and what is the best way to do things, okay? But this is a very good example that relying on p-value alone oftentimes give you very bad results. So we should not do that, right? But before talking about what's wrong with this paper or what's wrong with this approach to publication, let's first talk about what p-value truly means. Let's go back to our foundation lecture. I'm going to bring you back to, again, a discussion of decision theory, right? There we go, okay? Decision theory. Now, I think I've already done this, but let me just try to go through really quick again. So y is a variable, has 0 to 1, two different values, and you don't know the true y. You are trying to predict y, so we can have y and a y hat here, right? So both 0 and a 1, 0 and a 1, and this is, and you have, okay. Now, how do we determine y hat? Suppose, what is the best prediction of y hat? If y has only two values, what is the best prediction? According to decision theory, the best prediction is, first of all, suppose you know py, the probability of y equal to 0 and the probability of y equal to 1. You know these two. Then what is the best prediction you can make? You should make a prediction of, you say y hat, sorry, you should make a prediction such that it minimizes the loss function. And the loss function here is 0 and a 0 here. There's some cost here. There's some cost here. Okay? And then if we're really worried about one of them, we can set cost really large. If we're really not worried, we can set the cost small. So you're all familiar with that. Suppose the cost equal to 1, meaning we are equally worried about false negative or false positive. Then we should predict y equal to 1 if the probability of y is larger than 0.5 and equal to 0. Sorry, okay? And 0 if this probability of y equal to 1 is small, right? So that's all familiar with you. So when it comes to, let this y be our null hypothesis, okay? So null hypothesis can either be true, so the 0 will be true, this will be false, and false just means we accept H1, right? So we have false here, and we have true here, right? So this is your prediction, or you can think about this as your final decision with regard to the hypothesis. Okay. Now, this is true. In this case, we have the underlying null hypothesis true, but you reject it. Okay. When it's true, now is true, but you reject it. That's called a false negative error. And when you reject something, it's when your test result is significant, right? Okay. So this actually, when your test is significant, you reject it. You accept H1. correct? So in this case, you should not accept H1, but you should not reject H0, but you reject H0. That's false negative. What kind of error is this? This is also called type 1. Very good. Now, this is the case where you should reject, but you fail to reject. Right? Your result is insignificant. Right? So this is called a false positive. So now here, it may cause some confusion because it's called a false positive, but it's actually insignificant. That's just because of the way we talk about these, right? So the false positive is type 2. Okay, so you should, the probability of y equal to 1, now if you equally care about these two, then you predict y equal to 1. When you predict y equal to 1, it means you accept the null, or you fail to reject it, right? So you accept the null if the probability of y equal to 1 is larger than 0.5, right? Okay, or you reject it, if the probability of y equal to 1 is smaller than 0.5. However, if I mainly worry about type 1, so I mainly worry about when the underlying H0 is true, but I reject it. So it's not significant, but I say it's significant. I really worry about this case. Then I should put a very large cost, right, here, and put a small cost here. When I do this, the threshold, this is the threshold. The threshold go up or go down? It goes down, right? Because you do not want to predict y equal to 0 very easily. Because if you really worry about making this mistake, you should make it really hard to predict y equal to 0. Okay? So in other words, you should only predict y equal to 0 if this probability of y equal to 1 is really, really small. Okay, it's really strong evidence that it's not equal to 1. And then you do y equal to 0. So what you can do is smaller than 0.05, right? And that's the p-value threshold that we talk about. So in other words, the reason why, and that's the question I asked last time, the reason why we set the p-value to be a very small threshold is because we really worry about type 1 or false negative in this case. With only one trick, not trick, but with only one difference between this analogy and the true p-value we use, which is what? In this case, our decision is based on the probability of y equal to 1. Let's change y to h, okay? So our decision is based on the probability of h0 being true, okay? B is equal to true, right? So whether I want to accept or reject the null hypothesis h0 here is based on my understanding about the probability of h0 being true. But that's not the p-value. So here's my p-message, right? The p-value is not the probability of h0 being true. So according to decision theory, the best way to accept or reject the null hypothesis, the best way to do this is based on your understanding about the underlying probability of h0 being true or not. But p-value is not the probability of h0 being true or not. What is p-value? Let's go back to the definition of p-value, right? Okay. The p-value is conditional on the null being true, the probability of seeing an extreme or large t statistic. So let me use this as, let me use D. So D means large t statistic, okay? Large t statistic. Well, actually, because t statistic is computed on the data, you can think about D as basic data, okay? So the idea is, if null hypothesis is true, if it's true, what is the probability that I see my current data? I observe my current data. That is the meaning of p-value. So p-value could be understood as the probability of seeing my data conditional on h0 being true. but that's not what we actually, that's not the best, that's not what we want from a decision theoretical perspective. From a decision theory perspective, what we want is this. I want my decision to be based on the probability of H0 being true, conditional on the data I see, right? After seeing this data, what is my understanding about the underlying probability of H0 being true? If H0 is very likely to be true, I accept it. If H0 is very unlikely to be true, I reject it. So decision should be based on this one, okay, according to decision theory, not on this one. But this is the p-value. Okay. So what is the connection between p-value and the probability of H0 conditional on D? By the way, we can talk about why conditional on D. Conditional on D means after I see the data, what is my belief about H0? In theory, you can always define two things. We can define PH0 and P0 conditional on D. So PH0 could mean our belief about how true H0 is before seeing the data. And this one could be our belief after seeing the data. Now, have people ever heard of Bayesian terms, right? In Bayesian terms, this is called, what are these called? Do you know? Yes. This is called prior. This is called posterior, okay? Right? So this is my prior belief of H0 being true before seeing the data. This is my posterior belief of H0 being true after seeing the data. Okay? And now, in general, not in general, but we can always write this very easy Bayesian formula, which is the my posterior belief. After seeing the data, my belief about H0 probability is equal to, I can do this, right? The probability of H0 times the probability H0 times the probability D conditional H0. Right? We flip them, divide by the total probability D, right? So that's just the basic Bayesian formula. Now, what you understand, what you can see from this formula is that this is p-value. The p-value is the probability of observing the data conditional on H0 being true. But this is actually what we want. This is what decision theory says we should want, is the probability of H0 based on D. And we should form decision based on this probability. The difference between them is mainly, you can think about the probability D as simply a normalizing constant. So the difference between these, between the p-value and the probability of H0, is our prior probability, right? This is what we believe how likely our H0 is true before seeing the data. Together, if we multiply this prior probability with the p-value, then we get the posterior probability. Okay? So this prior belief can mean a lot. What we believe about this H0 before seeing the data could have a large impact on the posterior belief, obviously. So you can think about this Bayesian formula saying that finally what we believe, after seeing the data, what we believe about the H0 is a combination of two things. The first thing is what we believe before seeing the data. The second is what the data tell us. So you can think about p-value as what this data alone tells us. But in the end, what your belief about H0 should be a combination of before and this data. Okay? That's the understanding. Okay, so that brings us to this observation, which is what happens if the probability, if you believe H0 is very, very likely to be true before seeing the data. Okay? Your prior belief, your prior probability of H0 is really large. Then even if your p-value is very, very small, your posterior belief should still be very large. Correct? Okay, go back to this is a normalizing constant. Right? Forget about it. If this is large, but this is small, this could still be large. So even if p-value is really small, like below 5%, that looks like it's very unlikely here. But before seeing the data, we all believe that H0 should be true. Then the effect of p-value on my posterior belief should be just to decrease this. So the effect of p-value will be our posterior belief will be slightly lower than this one, because we adjust, right? Because the data tells us, look, it's not that likely, so we downward adjust our belief, but the belief should still be pretty large in nature, right? Okay, so let's do a simulation, right? I'm going to assume that I strongly believe H0 to be true. So I have a 90%, right? 0.9 prior belief on H0. And then I'm going to make some other assumption like H1, D equal condition H1. But regardless, here's the result. You can see that this is the p-value and this is the posterior probability of H0. Now, I would say this is the true probability that we should base our decision on. But this is the p-value. Look at the relationship. When p-value is 0.05, okay? So when, hold on. Let me see how to interpret it. Yes, p-value is here. When p-value is 0.05, that's a very small p-value. The true posterior belief is 0.35, right? 35%. So according to p-value, we're significant, right? We should reject H0. But according to the posterior belief of H0, we should not reject at all. Correct? So if we reject or accept based on the posterior belief, not based on p-value, then we should definitely not reject. But p-value is very small. Now, if p-value is, what if we reject H0 based on posterior belief? Then suppose we reject H0 if the posterior belief drops below 5%. Then what is the p-value? The p-value is 0.004. It's 0.4%, not 5%. In other words, if we want to use p-value to reject or accept, we should only reject when p-value is smaller than 0.4%, not when p-value is smaller than 5%. The threshold should be much, much lower, not 5%. Okay? Right? So that brings us to the moral here, right? The moral is the lesson, right? The lesson we are trying to say is that when the alternative hypothesis is highly unlikely, when H1 is very unlikely, H0 is highly likely based on my prior belief, then ideally, we should need the p-value to be much lower than 0.05, okay? Much lower than 5% as a threshold. The threshold should decrease a lot. We should only accept H1 based on extremely strong criteria, not a 5%, but probably 0.005%, right? Okay. So that's one lesson. The second lesson is how do we actually think about p-value? I would say the best way to think about p-value, of course, p-value, you can think about p-value as the probability of t-statistic, observing this t-statistic conditional on H0 being true. You can always think about this technical sense, right? But I would say intuitively, the best understanding of p-value is the probability of H0 being true if we discard prior belief, if we don't consider prior belief. So in other words, p-value is the probability of H0 being true based only on this particular data set. That is, we do not consider any prior belief. Our knowledge purely comes from this H0, from this data set. Then p-value is the probability of H0 being right? So if we know nothing about this subject before this data set, then our p-value is the probability, okay? Because we just get rid of this probability H0 because we know nothing about H0 before this data set. So p-value is the probability of H0 being true, conditional, right? Not conditional, but based only on my data set. An analogy is this, right? Suppose I want to know if a coin is biased or not. Okay? Now, here's the scenario. I have flipped this coin already. I've flipped this coin 1,000 times. And 500 times its head, 500 times its tail. So that's my history, okay? That's my historical data. There's 500 times tail, 500 times head is my prior belief. Now I'm going to do a new experiment. In this experiment, I basically flip the coin twice. And then both times it's head. So, what do you say about this coin? Is this coin biased or is this coin unbiased? That depends on whether you only look at this two-flip experiment or if you look at the entire history, right? If you look at the entire history, 1,002 times we flip the coin. 502 times its head, 500 times its tail. It should be what? It should be unbiased. But if you only look at this one experiment, which there are two flips, both are head, and you don't consider any prior knowledge, then you would conclude that this coin is biased. So if you only do that, that's p-value. That's making decision based on p-value, because p-value only considers the data set itself without incorporating prior knowledge. But if you ever incorporate prior knowledge, then it's a different story, right? Now it turns out that in real research, in any subject that we do research on, we typically have a lot of prior knowledge. Human beings have already done thousands of years of thinking and research and other things on each particular topic, right? So we have a lot of prior knowledge. If you don't use that, and if you only reach conclusion based on a particular data set, then you are going to reach some pretty you're likely to reach some pretty outlandish conclusions. That's why that brings us back to this paper, right? So this paper is about whether people can sense the future, can feel the future. Now, this is a subject that we human beings have thousands of years of observation and thinking, right? Obviously, throughout our history, except in ancient times, right? In ancient times, people think, we can do whatever. But obviously, so far, our entire civilization and our science and everything suggests that we cannot sense the future. And that is our prior knowledge. So our prior knowledge strongly suggests that H0 is true. H0 means we cannot sense the future. So our prior knowledge strongly says H0 is true. So in order for you to prove this is wrong, to accept H1, you should what? You should have extremely, right? Your evidence should be extremely strong, in other words, to refute thousands of years of prior knowledge. Not some p-value below 5% only. It should be p-value below like 10 to the minus 10, right, percent, not 5%. Okay, based on a small experiment. But in reality, what this guy did a small experiment and calculate some p-value and find out it's below 5% and publish it, right? So this is what truly going wrong in this approach, okay? Right? So in other words, now we'll talk about many other lessons in the future, but this is a very good example how p-value is misused in scientific research because people over-reliance on them as the only criteria to judge whether your results are solid or not. And the publication decisions are made on it, leading to many bad research examples like this. Okay. Do you have more time? Yes, I have more time. So let's talk about p-value as sample size. I just want to mention some other problems with p-value, right? Obviously, another example is sample size. What happens when your sample size is small? There are two things happen when your sample size is small. The first thing happen is your p-value is more likely. Everything else being equal, your p-value is more likely to be large. So you're more likely to be insignificant results. And the reason everything else being equal, right? Meaning the result is when a sample size is small, you lose power. Okay? The power of your test goes down. And by power, it means the probability of correctly rejecting your null. Okay? So when each one is true, the probability of accepting each one. So that's one thing. The second thing happens, so people tend to think, okay, in small sample, it's harder for me to get statistically significant results because my power is low. Well, that's actually not the whole story. Because sometimes when your sample size is small, it's also easier to get statistically significant results. It's also easier for a p-value to be small, and that's because our p-value calculation is based on this formula, right? Again, let's go back. It's based on this formula, and this formula is only correct in large sample. Okay, it's an asymptotic result. It's not a small sample, finite sample result. If your sample is really small, this formula is incorrect, meaning the standard error you calculate is unreliable. So it can go both ways. Okay. So if your sample size is small, you could also get very bad estimate of a p-value. And based on this very bad p-value, sometimes you're going to get statistically significant results when you should not. That's another way that small sample can happen. So that's a limitation. You can also say, okay, so let's only do research when n is large. Well, if you have really large data set, if n is really large, what happens? If n is really large, your beta had converged to beta star, right? Remember, beta star is the underlying, like the true beta in the underlying population. But if a data set is really large, then it's almost like the underlying population. So it's already beta star. So why do you even do hypothesis testing, right? there's no point of doing hypothesis anymore, right? No point of calculating p-value because it's already a very large data set. Okay, so that's why a lot of computer scientists working on extremely large data set, they don't worry about inference at all. Right? You look at a paper, they very seldomly ever talk about p-values in the statistical inference because their large data set is extremely large, and there's no point of talking about it. Well, first, another reason is they don't even have a formula for whatever complex models they're doing. So so in general, I would say, right, this, as a general lesson in this semester, just don't trust p-values calculated on small samples. Okay, just emphasize. Right, don't trust p-value calculation. Yeah, actually, I could go more extreme and say don't trust anything on small samples. Right? In small samples, everything goes bad. Right? You have bad generalization. We already talked about the VC generalization performance. Right? You have bad generalization. The p-value is the formula is not reliable, etc. And that's why. So this is again taken from Andrew Xiamen when he criticized psychology. These are the research based on psychological science, another top journal in psychology. And these are actual research published in one of the in the journal, one issue of the journal. And here are the research published: turning body and self inside out, visualize heartbeats, etc., etc. The sample size 17. So people did experiment involving 17 people, and they have significant p-value, and they publish in the top journal in psychology, right? And this is 57, this is 42. These are all pathetic, right? In a sense, but so in other words, just simply look at the sample size alone says that we probably should not ever trust whatever results they get, right? And here's a lovely quote by Xiamen and his co-author Loken. That says, the concept of p-value was originally developed by Ronald Fisher in the 1920s in order to what? In order as a means to protect researchers from declaring truth. Right? The reason why Ronald Fisher ever came up with the idea of calculating p-value is to protect researchers from declaring something based on patterning noise. Okay? We should only declare something is not equal to 0, has a significant effect if we're really confident, right, below 5%. That's the original idea of p-value. In ironic twist, p-values are now often used to give credence to noisy claims based on small samples. The idea is, initially it's going to protect researchers from making mistakes. But nowadays, oftentimes when it's misused, it's allowing researchers to make incredible claims because they happen to get a p-value below 5%. Right. Okay. Now, we're running out of time. So on Tuesday, I'm going to talk about 2 more misuse of not only p-value, but also the way that people do research, including data spoofing that we just talked about. So that's going to be next lecture. Okay, we'll continue on Thursday.